did you see? Something evil?
Excitement, confusion.
So to establish this idea of the trapezium rule, we're going to look at an example, and it's a definite integral from pi over 6 to pi over 3 of cot x integrated with respect to x. And what I'm asking you to do is not strictly true. I'm asking you to evaluate that without finding an antiderivative. But as you'll see, you cannot evaluate it exactly. So we are going to see how good an approximation can we get without finding an antiderivative. Our task is to find the area beneath this curve, because we're asked to find the integral from pi over 6 to pi over 3 of the curve y equals cot x, with the twist that we cannot use an antiderivative. So we need to go to the next best thing, which is we need to use a geometric shape. Now I'm going to do this because I know that the definite integral is directly linked to the area under the curve. Okay, particularly in this situation, because y equals cot x between pi over 6 and pi over 3 is purely above the x-axis. So the definite integral and the area are the same thing. If I draw a line from this point to this point where the y values are, you can see clearly it makes a trapezium shape. So to get not the exact answer but a very close approximation, we can just calculate the area of this trapezium, and hopefully that will give us a reasonably good answer. Let's do that. I'm going to call the region that's bound by this line which I've constructed here, the straight line, the line x equals pi over 6, the line x equals pi over 3 and y equals 0. That region that's bounded, which is just slightly different to the definite integral, we're going to call that R. And you may be thinking, okay, how good is this estimate going to be? And is there a way we can make it better? Well, we can. We'll do that later. Let's calculate R. Now, R as in the area of the trapezium. Well, we know the area of a trapezium. We did this at GCSE. So we just need to find a few of the values and then we can substitute them into the formula. I'll just make a note of the formula here. So the area of R is just going to be a half of h times a plus b, or a plus bh, however you want to call it. Remember that a and b are the two parallel sides. I'll label those on here. So this could be A, this could be B. It doesn't matter which way you do it, of course. You can do it either way. And h is the distance between the two parallel sides, and that distance has to be perpendicular. And we know it's perpendicular because x and y are at right angles to each other, so there's no problem there. So let's find out what h is first of all, and then we can sub everything into the formula. So h is going to equal pi over 3 subtract pi over 6, which essentially is 2 pi over 6 subtract pi over 6, which is just going to give us pi over 6. So we've got our h, that's the distance between the two parallel sides. We can substitute everything now into the formula for the area of a trapezium. Okay, so let's do that. So the area is going to be 1/2 of h. Now h is pi over 6. And then I'm multiplying that by the sum of the two sides. Now, do we have those values? Well, yes, of course we do. Remember that these are coordinates here, so I'll just indicate them. So this point here and this point here are coordinates on the curve, and the curve is the cotangent cot of whatever the x value is. So the distance a must be the cotangent of pi over 6, and the distance b must be the cotangent of pi over 3. So let's sub those in. So a, that's going to be cot of pi over 6. Okay, and we're going to add b, which is cot of pi over 3. Cot of pi over 3. Right, okay, so let's close that bracket. Great, now we're going to have just a bit of evaluating to do now to get the area. So this is going to equal, let's fill this in. Well, half of pi over 6, that's pi over 12. Let's write that in. Okay, and then cotangent of pi over 6. Well, pi over 6, of course, is 30 degrees. Okay, the tan of 30 degrees is 1 over root 3. So if we reciprocate that, that's just going to be root 3. But you can do that on your calculator if you're not sure. So this is going to be root 3. Then we take the cotangent of pi over 3. Again, if you do this on your calculator, and that's going to give you root 3 over 3. When I say do it on your calculator, what I mean is you can find the tan of the angle and then reciprocate the fraction. You might want to do a bit of rationalizing surds as well, okay, as I've done here. Okay, but I'll leave that work to you. Okay, and now we can combine the amount of root 3's we have. So this is going to be pi over 12 multiplying 4 lots of root 3 over 3. And the final answer, the bit of cancellation. So I have 4 over 12 and well, the 3 won't do anything, but here and here, so I've got 1 and 3 like that. I've just muddied my red, but never mind. And that's going to leave me with pi root 3 over 9. Now then, so that's the area of the trapezium. So the trapezium here that I've constructed. Is this an overestimate or an underestimate? That could be a good question. Well, if you look at how it's constructed, because this is a convex curve, when I draw the straight line connecting the 2 points on the curve, every point on that line, apart from the points where they coincide, is above the curve. So this is clearly going to be a slight overestimate. We can check this because we actually calculated the true value of the integral in the preparation task. Okay, if you remember, I'll just write this down. It was log of root 3. So we can tell just by a bit of intuition and from the diagram that this must be greater than or equal to. We'll put equal to if it's perfect, but it won't be. But it's definitely greater than or equal to the natural log of root 3. Okay, and I know that without even doing anything on the calculator because of the nature of the definite integral and the way the trapezium was constructed. Next, you might want to say, okay, well, we know this is an overestimate, but by how much? And we have the luxury here, we have the actual answer, the exact answer is log of root 3. Well, we can calculate a percentage error, which is a nice way of summarising how good or bad our estimate is. Now, if you remember, if we take the value that we calculated our estimate, okay, and we'll subtract the real value. I'll do this over here. So we're going to have pi over 9 root 3 subtract the natural log of root 3. Now that's the difference between the estimate and the actual as a number. But compared to what? Well, we compare this, so we divide it by the original actual answer. So if we divide this by the natural log of root 3, then this puts the numerator in context, doesn't it? So we know by how much are we out now. Now let's convert it into a percentage. So we'll put all this in brackets. I'll put it in square brackets because it's such a big fraction, like that. And now if I multiply this by 100%, like so, now this is going to give us a percentage. Now, if you do this on your calculators, you should find you're going to get 10.1%. Now, this means that it's an overestimate by 10.1%. Is that good or bad? Well, it's reasonable, but you want to ask the question now, how can we make this approximation better? And we're going to look at that next. Following on from the first part, where we calculated a reasonable estimate of the definite integral, we're going to refine the model, and this time we're going to split the definite integral into two trapezia of equal height. We can then, once we've calculated the area of those two trapezia, we then have another approximation for the definite integral, and we can compare the accuracy with the previous example. Next, in case 2, we have the same diagram, and we've already got a reasonably good approximation of this definite integral under our belts. So a natural question would be to ask, well, how can we extend this idea? How can we make our approximation even better? The obvious answer is to introduce more trapezia. And what we're going to do now is we're going to see how good will this approximation be if we divide our definite integral into two trapezia. So we're going to do that next. Now I've introduced a new line which will bisect the points pi over 6 and pi over 3. And this has now split our definite integral into two trapezia. And you can already see, of course, that because we have this extra coordinate here that we're going to be dealing with, the approximation looks even better. Even on a rather crude sketch like mine, you can tell this is going to give us a better approximation. The question is, can we work this out mathematically? Next step, we're going to calculate the areas of these two trapezia separately. Right, now what I'll have to do is first of all work out what this point is here so that we can establish what the height of the two trapezia will be. Remember, I've placed this exactly in between pi over 6 and pi over 3 to make sure that the two trapezia have the same height. Let's label the trapezia and essentially give them a name. So we'll call this first one number 1, and we'll call this one number 2, like so. So let's work on number 1 first, but before we do that, let's establish what this coordinate is. So as I said, this coordinate here is going to be the midpoint, if you like, of pi over 6 and pi over 3. So I'm just going to take the mean average. So let's take the average of those 2 points. Then we have pi over 6 plus pi over 3, and we'll divide that by 2. This is going to give us essentially 3 pi over 6, which is pi over 2. Just changing them both into 6, divided by 2. And half of pi over 2 is, of course, pi over 4. Right, so I can now introduce this new coordinate. This is pi over 4. I'll write it on the diagram. And this means we can now determine what h is. Okay, so h is going to be the difference between pi over 6 and pi over 4, or in a similar fashion, pi over 4 and pi over 3. It doesn't matter which one you use, you should get the same answer. So h is going to equal pi over 4. I'll use shape number 1. Subtract pi over 6. We can convert these into 12ths. So 3 pi over 12, subtract 2 pi over 12, which is going to be pi over 12. So there's the height of our trapezium, perpendicular height. Great, so we've got our h. We're now ready to use the formula for the area for trapezium 1. Remember, of course, a is the cotangent of what you get when you sub in pi over 6. So the b in this case, which would be this side, I just sub in pi over 4. So just to make it a bit less misleading, I'll just erase this b here. Okay, so for trapezium 1, the b is going to be this side that I've added in green. So let's calculate the area. So the area of 1 and I'll do the one in red, I'll just be consistent with that. So area of 1 is going to equal, it's going to be 1/2 of h. I'll put the h in first. So that's pi over 12 this time. And then we're going to put in a plus b, so that's going to be cot of pi over 6. We used that last time, of course, in case 1. Cot of pi over 6. And then b, so that's going to be cot of pi over 4. And we'll close that bracket. Great, now we'll just do a little bit of working out here. So this is going to equal, so I'll multiply through by 1/2 here, so that's going to be pi over 24. Alright, and I want an exact answer, so let's just think carefully about this. We know what cot of pi over 6 was. We did it last time, that was √3. Let's put that in again. Okay, and cot of pi over 4, well, if you're not sure about your cotangent values, remember that tan of pi over 4 is, of course, 1. Cot is the reciprocal of that, so it's just going to be 1. Okay, and we have a rather nice exact answer for the area of 1. I'll just write that as an area, so that would be units squared. We don't know what the units are, we'll just acknowledge that this is an area. Right, okay, now we can move on to trapezium 2. We have h already, so again it's just a case of substituting in all the values. I'll do this over here. So the area of 2 and I'll just talk you through the steps, of course. So area of 2 this time. So this is going to be 1/2 h. Now you can just check this if you want to. If you do pi over 3 subtract pi over 4, we can use 12ths again. So pi over 3, of course, that would be 4 pi over 12 subtract 3 pi over 4. Again, we'll give you pi over 12. So you can check that if you want to, but if everything's okay, it should be the same. So pi over 12, perpendicular height, and then we sub in our two sides. Again, I probably should just remove that a, just so we don't get confused what we're talking about. So the a there. So the a in this case is what you get when you sub pi over 4 in. Now, I've already used it. Remember, this is the side in the middle that comes up twice, as we saw in the preparation task. So I know that's going to be 1. I'll write in cot of pi over 4 because this is for your notes, of course, and you want to see all the working out. So this is cot of pi over 4. Again. And then we're going to add cot of pi over 3 for b. And we close that. Alright, so a little bit more working now. So this is going to equal, again, pi over 24. And then we evaluate these. Cot of pi over 4 is, of course, 1. And then cot of pi over 3, as we saw in the previous question, is 1 over root 3, but I will rationalise that in my head. So that's going to be root 3 over 3. So you can recycle these answers, there's nothing wrong with that. And nothing really to simplify here, so I'm just going to write that as units squared. Okay, so next we're going to put the areas together and we're going to check the accuracy of our answer. Now, I've just summarised what we've just found, so I've just written out the areas of 1 and 2 separately. We need to find the total area. Now that will be the approximation of our integral. And remember, we have the exact answer, so we can test how good this approximation actually is. Alright, so let's add these together. And it might be a good idea, I might just expand both these expressions and see if there's any like terms we can collect. So total area. And let's sub everything in. So I'm going to multiply out 1, so I'm going to have pi root 3 over 24. That will be the first term. I'm just multiplying out the bracket, plus pi over 24, of course. So that's the area of 1, and then I'm going to add the area of 2, so that's going to be plus pi over 24 again for the first term, plus pi root 3. Now I'm going to write it as 24 times 3 on the bottom. I'll explain why in a second. There we have. So we've got 4 terms. Can we collect any like terms? Well, yes, of course we can. We have 2 lots of pi over 24. So I can collect those together. That's going to give us 2 pi over 24, which is pi over 12. So this is going to equal pi over 12. And the reason why I didn't multiply this out is because you can see we've got pi root 3 over 24. I've got 1 amount of that. And here I've got 3 multiplying the denominator. That means I've got 1/3 as much. So essentially I've got 4/3 worth of pi root 3 over 24. I'm going to write that in and then we'll see if there's any cancellation. So I'm going to have plus 4 pi root 3 over 24 times 3. This is because I'm not using the calculator directly here. Cancellation. Well, yes, the 4 and the 24, there's some cancellation there. So I'll just acknowledge that. So there we go, that's 1. And we've got 6. And there, it's dirtied my red, unfortunately. And let's put in our final answer for this. So this is going to be pi over 12. Remember, it's going to be exact. Plus pi root 3 over 6 times 3, which is 18, and this is going to be in units squared. So the question is, how good is this answer? Well, we can take a percentage error calculation for this. We're going to do that next. Right, so you might want your calculators at the ready to check this. Percentage error. So let's take the difference between what we have and the exact answer. And we know, because of the convex shape of the curve, this must be an overestimate. So if I take the difference, it's going to be this amount here, subtract ln of root 3, and we know that's going to be a positive amount. Let's do it. So the percentage error, make sure I can squeeze this on here. So percentage error So I'm going to do pi over 12 plus pi root 3 over 18, subtract ln of root 3 all over the original, or the actual definite integral value. So that's the fraction, and then I multiply this obviously by 100%. Let's put some brackets around this. So multiply that by 100%. Now you can start keying this into your calculator if you like. The answer is approximately, and you can't see that, let me rewrite those equal signs, or the approximately equal sign. Maybe I was a bit optimistic with the space. Okay, I'll put it in here. So it's going to be approximately equal to, and 2.69%. Now, just think how much of an improvement is taking 2 trapezia than using a single trapezium. The improvement is quite considerable. We've dropped by approximately 8%, maybe a bit less than that, but we've got a much better approximation. As you can probably tell, the more we refine this model, i.e. the more trapezia we introduce, the better this approximation is going to get, until you get to a point where you cannot distinguish between the actual answer and the approximation. Okay, it all depends on the accuracy you want. Let's look at the implications of this, and we're going to generalize this result next. I want to give you a demonstration of how the trapezium rule actually works, and by extending the cases from 1, 2 to 3 and more, we can see the power of this as an integration tool, a numerical integration tool, because the more trapezia we have, the better and better the estimate is going to be. And you'll see this in a moment. What we've got here is the curve y equals cot x. This is the black curve here. And the exact answer, which we've already calculated, that's the integral from pi over 6 to pi over 3 of cot x with respect to x. This is the answer, log of natural log, of the square root of 3 given to 5 decimal places. So this is correct to 5 decimal places. The trapezoidal sum simply means the trapezium rule. You can use either term interchangeably, and this is what we calculated in the first case when we had 1 trapezium, and that represents the pi root 3 over 9, which you calculated in that case. And this was the error that we also calculated, and we wrote it as 10.1% to 3 significant figures. This is to 5 decimal places, of course. So even with 1 trapezium, and as you can see, it's an overestimate because the curve is convex. But as we increase the number of trapezia, we'll see this error drop, hopefully. So let's set this going. We'll do it slowly. Okay, keep your eye on the error and the trapezoidal sum. All right, let's just pause. So straight away, we've gone from n is 1 to n is 12. This is set to go all the way up to 100. But as you can see, the error has plummeted. It's barely, well, it's 0.07%, which is a vast difference from 10%. And we can see this trapezoidal sum converging on the exact answer. All right, let's keep it going, maybe speed it up a little bit. Okay, now I've just paused it just before the end. Let's run it. All right, so that's right at the end, and the trapezoidal sum, it's converged to the 0.54931. That means it's correct to 5 decimal places, and the error is barely registering. And you can set the n to as much as you like, and if you take the limit, of course, as n tends to infinity, then you get the exact answer. But this allows us to do vast amounts more integration than would be possible if you want to evaluate definite integrals, of course, and we're going to explore that in a moment. Now that we've had a look at two cases, one case where we have just a single trapezium approximating the area of the definite integral, and a slight refinement where we use two trapezia, we can now generalize this idea, and let's consider a continuous curve y equals f of x, as you can see in the diagram. And what I'd like to do is to approximate the area R under the curve, not by finding an antiderivative, of course, but by using an approximation. What we've done here is we've divided the interval a, b, which are the lower and upper limits of the definite integral, into a set of n trapezia of equal height. And now we have this established, we can then use some algebraic techniques and come up with a rule that we can apply to future examples. What I'd like to do now is to walk you through the derivation of the trapezium rule, which we're going to do. We've looked at one particular example where we're using trapezia to approximate the area, and that was y equals cot x. And we saw that when we had just one trapezium, we had a reasonable approximation to the definite integral, but when we started to divide the interval from a to b into even more trapezia, well, namely 2 trapezia, the approximation got better, and you could see intuitively that this was going to get better and better the more trapezia you have. Now what I have here is just some continuous function f of x, and what we're interested in is the definite integral between x equals a and x equals b, which will in this case calculate the area under the curve. Now we can represent, of course, the area under the curve because f of x is purely above y equals 0, or the x-axis, so we can represent it like this. So this is what we're interested in. So the area, which we will call a, is equal to the definite integral from a to b of f of x with respect to x, of course. All right, and what we'd like to do is we want to approximate a. So we're going to find an approximation for a, and there's various reasons why you'd want to do this. I'll get more into that later, but first we're going to look at how we can actually do this. And the first thing we're going to do is to say, okay, we've tried one trapezium, we've tried 2 trapezia, what about n trapezia? So we're going to divide our area, or as best as we can, we're going to divide the area under the curve into n trapezia, and then let's see what happens after that. What I've done first is I've divided up as best I can the area between A and B into trapezia of equal width. And you may look at this and say, well, why have you missed some out, or what's actually going on? It looks like it should be 6 trapezia. This is actually the hardest part of the derivation to get across. This represents any partition of the area. So just you have to use your imagination a bit here. There are, in theory, n trapezia, and I've just done it like this so it will be clear on the diagram, and you can see from the table, when we see the table, how it all fits together. So it's a generalization, okay? So don't take this at face value is what I'm saying. Now we've divided the area up into trapezia, we can see it's not going to be perfectly accurate. There's clearly space between the curve and the straight edge I've introduced here. But once, of course, we take limits, if you wanted to do that, as n tends to infinity, your number of sides, you'll see that this will tend closer and closer to the actual definite integral. Now then, what can we do with this? Well, the first thing we need to establish is the width of each of these trapezia. And it's actually quite straightforward. Remember, we referred to the width as h in the previous cases. Well, if each of these has a width of h, let's label that. So let's just take any particular trapezia, so it's got a width of h here. How do we find that? Well, we've got a distance that we know. We know that the distance, if you like, I'm putting distance in inverted commas there, the distance from A to B in the x direction is clearly going to be the difference between the values A and B. So B being the larger value, A being the smaller value. Now, that will give us the distance between the 2 points. And I want to divide this distance into n equal pieces. So that's exactly what we do. I just write that algebraically. So h as the height of the trapezium, or any of these trapezia, is simply going to be b subtract a divided by n. And just make a note here, this is very important, n is going to be the number of trapezia. Yeah, please make a note of that. Okay, so we've got that. Now, the other thing we need to know is what the parallel sides are going to be. Remember, we're going to use the parallel sides to establish the area of each of these trapezia separately. Well, the easiest way to do this, and you'll see this in a lot of questions, is to use a table. So that's what we're going to do next. What I've done here is I've introduced a table that is provided for you in the notes, but I want to go through the thought process in some detail. So the first row is going to be the x values, which are the nodes, if you like, or the edges of each of the trapezia. The f of x are the corresponding values of the function, which in turn gives us the y value. The y and the f of x are the same value. It's just a case of labeling. Now, the first x value that we're interested in is a. Okay, this is the lower limit of our definite integral. So let's put that in our table. So a goes in here. Okay, if I substitute a into my function, obviously I'm going to get f of a, like that. And then this is going to be what we call y naught. This is the first y value. And we start at 0 because we want the number of trapezia and the number of edges, or the numbering of the edges I should say, to be in sync. If I start with y1, then we'll have to do some adjustments to the number of trapezia and the y values, and it gets confusing. So that's the first column done. Now, I want to talk about the x values in a bit more detail now. We need to identify what the next x value is going to be, and this is going to be the adjoining parallel side for the first trapezium. Now, as you remember, as we established earlier, we said that the height of the trapezium, or every trapezium, is going to be h. So this means that there is a distance of h between A and our next x value. So let's indicate that on the diagram also. So this is going to be h. Okay, now that means that to get from A to my next x value, I need to add h. So that's exactly what I'm going to do. So the next x value is going to be A plus h. Let's put that in. So A plus h, like so. And consequently, the function is going to be f of A plus h. And this is going to be our y1. Now what I'm going to do now is I'm going to label the y0 and the y1 on our diagram. So over here, this is going to be y0, and this is going to be y1. And as you can see, we now have enough information to work out the area of the first trapezium. That's very important. Okay, so continuing on with the trend, I've got A plus h. This is the point here where my nail is, and then the width of the next trapezium is also going to be h. So I'm going to indicate that on the diagram as well. So this is also going to be h. That means that to get from A to this point here on the x-axis, I'm adding 2h. All right, so this point here, in case you weren't sure what I was talking about there. So this is A plus 2h. Let's put that in. So this is A plus 2h. Okay, and now we've established the pattern, we're going to have A plus 3h here, and then dot, dot, dot. And then the final x value, well, our final x value is clearly going to be our upper limit. So we're just going to put B for our final x value, okay? There we go. Well, you could have said A plus NH if you wanted to. Now, consequently, I'll just fill in the rest. We're going to have y0, y1, obviously y2 here, like so, y3, continuation, and then yn, the nth side. And just to be exact, this is going to be f of A plus 2h, f of A plus 3h, alright, continuation, and then f of B. Okay, let's just finish labeling the diagram and then we can finish our derivation. So we've got y0 and y1 labeled. This process is going to continue. So the next side is obviously going to be y2, so let's put that on there. So this is y2, y3, and then remember the last side is yn, but if I just put yn on there, and obviously that's going to have a width of h, that's not enough information to work out the area of that trapezium. So I'm going to introduce y of n minus 1 here, although it's not in the table, but it follows the pattern. Okay, so the final trapezium will have the parallel sides of yn minus 1 and yn. Right, now we have all the ingredients we need to calculate an estimate for the area under the curve. Before we go into the final stages of calculating the estimate for the area under our generalized curve y equals f of x, let's just have a brief look at how the area of a trapezium in this situation is calculated. What I've done here is I've set up a generalized trapezium diagram taken from the area under the curve that we've just established, the curve y equals f of x, and as we saw on the diagram, we've labelled each of the parallel sides y with a subscript, and the subscript ranges from 0 to n. So this is also generalized on this diagram. We have y of I subtract 1 and then yi. And the subscript can take any one of the following values. I'll just jot those down. So I can be anything from 0, 1, 2, all the way up to n. In fact, there are n plus 1 edges or parallel sides. So there's n plus 1 of these edges. And the reason is, of course, is because we want n trapezia. N trapezia, therefore we must have n plus 1 edges. If you're not convinced by that, just draw a few shapes out. So I'll do this for you. If I just draw 2 trapezia really quickly, it doesn't matter what shape they are, you can see that I've got 3 of the parallel sides like that. Okay, but I have 2 trapezia. If I had another trapezium on the edge like that, I now have 4 parallel sides and 3 trapezia, and so on and so on. So I'm always going to have one more edge than the number of trapezia. Now then, let's have a go at calculating a generalized area of the trapezium, and then we can apply this to our sum. Now you remember from GCSE, the area of a trapezium is a half multiplied by the perpendicular distance between the 2 parallel sides, in this case called h. And remember, h, because it's perpendicular, must make a 90-degree angle with the 2 parallel sides. These, of course, are the parallel sides. So it's half of h, and then I add the 2 parallel sides together. So my AI is going to be 1/2 of h multiplied by y of I subtract 1 plus yi. And if we do this for every trapezium within our total area sum, we will get the total sum as an estimate of the definite integral from a to b. We can now put all these ideas together from the table and from the formula for the area of a trapezium to write out the trapezium rule in full. Right, I'm not going to number the trapezia in this case, we're just going to go right ahead and do it. Now the area, remember, approximates the integral, or the trapezium rule will approximate the integral. So this is not actually going to be exactly equal to a, so I'm going to use an approximation. And something else I'd like you to be aware of is in the formula book, this is actually provided for you. And as you know, f of x and y are the same thing. So you may see this written as the following. So this would be equal to the integral from a to b of y dx. Okay, I just don't want you to get confused if you see slightly different notation. And in fact, we'll use this in the next part. Alright, so to actually calculate this, approximately of course, we're going to have the integral from a to b of y dx, like so, is going to be approximately the same as the sums of all the areas of all these n trapezia. Okay, so let's do the area of the first trapezium now. So that's going to be 1/2 of the height, and then we add the 2 parallel sides. So that's going to be y0 plus y1. Okay, so that's the first trapezium here. Then we're going to move on to the next trapezium. Now you can see the parallel sides are going to be y1 and y2. So let's add the area of that trapezium. So plus 1/2, the height is the same of course, of y1 plus y2. Okay, let's move on. Then we have trapezium number 3. So it's going to be plus 1/2 of h of y2 plus y3, close the bracket. Alright, and then let's just skip a few. Obviously we've used the 3 that are on the diagram. Let's be consistent. Now we're just going to have the same thing over and over again until we get to the final trapezium, which is this. So it's going to be plus dot dot dot, and the final trapezium's area, which is going to be 1/2 of h, and then I add the 2 parallel sides together. So this is going to be y of n subtract 1 plus y n. Does that just fit on? I may have got away with that. Just about. Alright, so that's just adding up each area individually. Now, you may have noticed we've got half h's everywhere, in every single area, because the height is the same in each trapezium. Let's factor out the half h all the way across. So I can put a straight equals now, because this is equal to the previous step. So it's going to be 1/2 of h, and let's do the factorising. So we're going to have y0 plus y1 from the first trapezium plus y1 plus y2 from the second trapezium. Okay, so I've taken care of this one and this one. Then I'm going to have y2 plus y3. Let's add that. Okay, and then plus the rest, plus yn minus 1 plus yn. Okay, let's have a look at what's going on here. Well, we have a single y0 at the front inside our bracket, and if you'll notice, we have pairs. So we have y1 appears twice because it's the second parallel side of the first trapezium, which means it's going to be featured in the area of the second trapezium, as we saw in the preparation task and in the previous example when we introduced this idea. And similarly, we have y2 appearing twice. Now y3 will also appear twice, because if I simply drew another trapezium here, I'm going to need y3 to calculate the area of that. I'm also going to have the same issue with y of n minus 1, because y of n minus 1 features in the area of the final trapezium, but also in the penultimate trapezium. So there must be 2 of these as well. I'll just put a mystery, well, acknowledge that it's there. There is going to be a grouping here as well. Now yn will not feature twice because it is my final side in my final trapezium. Okay, I hope that makes sense. So this means that I've got pairs, which means I can just collect like terms and write 2 of each. So this is going to give me 1/2 of h. Then we're going to have y0 on its own plus 2 lots of y1 plus y2 plus y3, and the trend will continue all the way up to y of n minus 1, but then the trend stops and we have only one of the final side, the final y value. Okay, and there we have our trapezium rule. And just to remind you, the h in this is generated here. It was the first thing we did. It's b minus a over n. So you may now be wondering, what is the point in using the trapezium rule when we can simply find an antiderivative using an integration technique, substitute in an upper and lower limit, and evaluate to get an exact answer? Well, the answer to that question is not all functions have an antiderivative, or at least not all functions have what we call an elementary antiderivative. And we're going to look at a few examples now. So in the notes I provided you with the first one, which is the square root. I'm going to type this in. So this is 1 subtract x cubed. And this website's really good. This is Integral Calculator. And you can just type in your function. You can even type in the limits if you like. So if you just click on options here, you can put your lower bound and your upper bound. And it will work out your antiderivative and evaluate it if you have limits and show you all the steps. It's really good. So let's click on go and see how it copes with this. So I'm not putting limits in because I just want to see if the antiderivative exists. Alright, let's have a look. Manual integration with steps. Oh dear, no antiderivative could be found within the given time limit. Or all supported integration methods were tried unsuccessfully. I think that's what happened. And it also tells you, note that many functions don't have an elementary antiderivative. This is true. This is good because it also gives you the graph of the function, and if the antiderivative existed, it would graph that for you as well. So no antiderivative there. So we would have to use the trapezium rule if we wanted to evaluate a definite integral with this. Let's have a look at the next one. Now, the next one I've given you, you may recognize, I don't know. So e to the power negative, and I'm going to put the letters in carefully here, x squared. This is the basis of the normal distribution. This is the Gaussian curve. And again, I'm not going to put the limits in. Let's see how we get on with this. So go. Let's see how we do. All right, it's tried. Manual integration with steps. Ah, right. We have an antiderivative. Now, this here, we have root pi over 2, and then we have earth x plus the constant of integration. Now, the earth, this is an abbreviation of the error function. And the error function is what we call a non-elementary antiderivative. If you'd like to know more about that, I'll put a link in the description for the video if you want to find out more about the error function. But it is based on the integral of e to the minus x squared. So once again, we don't have an elementary antiderivative. And you know from working with a normal distribution, you use tables to calculate probabilities. You can't integrate it. Okay, so let's have a look. After that, now we've done this, let's have a look at some worked examples, or a worked example using the trapezium rule, and we're going to use this as an example.
You have survived, barely, but you must now do the worked examples.
There's a lot of information in this worked example, and it's based on the idea that we have just been talking about, the fact that e to the power negative x squared does not have a non-elementary antiderivative. This does not stop us, however, from calculating very, very good estimates for the area under the curve using the trapezium rule. And we've defined the finite region R as bounded by the x and y axes and the line x equals 1, including the curve as well. And we've set up a table of values here for 5 x values that we're going to substitute in to our function and hopefully give us a nice estimate for the area under the curve. So there's a few things we need to do here. The first thing we're going to do is complete the table of values using the function itself, and then we can compute an estimate for the area under the curve using the trapezium rule that we have just derived, and that is featured in your formula booklet. And once we've done that, or you could be thinking about that now, we can establish whether this estimate that we've created is an overestimate or an underestimate, and we'll talk about that later. Okay everybody, right, so the example, the only worked example we're going to look at is the case for y equals e to the minus x all squared. What I've done is I've sketched the curve that you're given in the notes, and I've also written down the trapezium rule as it appears in the formula booklet. And one thing I also need to mention is it will also tell you how to find h. So there's no need to remember that either. So you're also told that h, I'll just include it here, is equal to b minus a over n, which n, remember, is the number of trapezia that you're using. You're also given a table of values, and the first task, of course, is to complete the table of values. So we'll do that explicitly. And all the values are going to be to 3 decimal places in here. Alright, so let's complete the table of values. Let's just also make a note of what information we have. Remember from the derivation we start with y naught. So the first y value is of course y naught, that goes here. This is y1. And y2 will need to be calculated, so will y3. Okay, and y4. And because we start with y naught, the final value I end with, that's the n that I have, and that's the number of trapezia. So I also know that my n is equal to 4. So there's going to be 4 trapezia in this approximation. Right, let's work out the values. So this is just a bit of calculator work. So y2, we'll do that here. So y2 is going to equal e to the negative, and when we put in our value, which is 0.5, so that's 0.5 for our x value, and that's squared, but squared inside the power, so be careful. And remember, of course, the negative's on the outside, so be careful with that. And this is going to equal, if you plug it into your calculator, 0.779. That's to 3 decimal places, which we're going to use for now. Okay, next we need to find y3. So y3, so same process again, we're just going to sub in 0.75. So y3, that's going to equal e to the power minus, I'll put it in green so we can see the substitution. So that's going to be 0.75 all squared in the power, negated, and then e to that power. So that's going to give you 0.570 to 3 decimal places. Please do check this on your calculators that you agree with those. Alright, so we've now got y2 and y3. I might as well fill those in the table. So we've got 0.779 and 0.570. If ever you're not sure, I mean, just check, do your answers make sense? I mean, we're starting at y equals 1 here, and clearly the values are decreasing. Just make sure your values do the same, and these seem to be pretty good. So next we're going to substitute into the trapezium rule, and we're just going to refine the trapezium rule a little bit to suit our example. So let's start using the formula. The first thing I'd like to do is to calculate h, and it's a bit of a giveaway really from the table. The h is staring at you, but I'm just going to work it out from the formula book so you know how to do it yourself. So remember, it's b minus a. B is your upper limit of your x value and a is your lower limit. So let's just indicate that on the table just to remind you. This is b and this is a. So if I do b minus a, let's just work it out here. So h is going to equal b minus a over n. We already established n was 4, so that's going to equal 1 minus 0 over 4, and we'll stick with the decimal format, so that's 0.25. And I've already said you can work this out from the table, because remember when we derived this, your second x value is a plus h. Well, to get from 0 to 0.25, you must be adding h, so hence h is 0.25. Anyway, it doesn't matter, it's just pretty easy in this case. So now I've got my h as 0.25, I've just added that to my list of values that I need. And we're going to just do a bit of refining of this trapezium rule. I don't need this kind of abstraction, I'm just going to make it simple because we're only going up to y4, which I've just accidentally scrubbed out earlier. So let's just put that back in. So there's y4. So let's write out the trapezium rule. And we're integrating from a to b y dx. Let's write it here. So the integral from a to b of y dx is approximately the same as, I'm not going to substitute anything in other than the n, just to show you how this works. So that's going to be 1/2 of h, large bracket. Now remember, y0 goes in first, plus yn. Now n is 4, so I'm going to put y4 in there, and that means those are the two values that only appear once, and they're on the outside because it's the lower limit and the upper limit evaluated in the function. So the rest of it I'm going to use twice, so it's going to be 2 lots of everything in the middle, so 2 lots of y1, y2 and y3. So let's put that in. So plus 2 lots of y1 plus y2 plus y3, and we'll close the big brackets. Great. Let's substitute in all the values. So I'm going to use a straight equal sign now because this is equal to what I've stated before. I'm going to drag it across a little bit because there's a lot of numbers going in here. So this is going to equal 1/2 of, now it's h is 0.25, let's sub that in. I'll put it in here, so 0.25 for h. There we go. Close that. And y0, that's 1 from the table that was given to us, plus y4 that was also given to us. This is 0.368. No problems there. And then 2 lots of the rest. So plus 2 multiplied by 0.939 plus 0.779 plus 0.570. Close that and close the bracket. Okay, now just check everything's in there. We've got the h in there, we've got y0 and y4 and 2 lots of these 3 values. Everything is in there. This is just going to give us a number for our answer, so let's evaluate it. So on your calculator, just plug all that in and you're going to get the following. So that's 0.74 to 2 decimal places. And we're asked to state whether we think this is an overestimate or an underestimate. Well, in a moment I'll show you the or a slightly better answer. But if you look at the shape of the graph, it's concave. Okay, so if you're joining up nodes on the curve using straight lines, it's going to underestimate the curve. Now I could just do this really crudely on the diagram. If for example this was just 2 trapezia, and it doesn't really matter, I mean the trend will follow for 3, 4, 5 and even more trapezia, but if I just use 2, I would have a node there, perhaps a point, and if I just split this into 2 trapezia like that, you can see it's going to underestimate the definite integral. So this is going to be an underestimate, so just make a note of that. And the reason is because the curve is concave on this domain. On the interval AB. I mean, you could elaborate a bit more, but that's the basic idea. It's a concave shape. All right, and then we're finished.